Welcome to Math for Wisdom. I'm Andrius Kulikauskas. Today, we are discussing a recent video, Sheffer Polynomials, Combinatorial Space for Quantum Physics. And you can see the main formula above that we'll be discussing. And so we'll go through the slides. If you'd like more information, go to mathforwisdom.com. Thank you to all my Patreon supporters. So this was an introductory slide, very complicated, but just to show right from the beginning that these Sheffer polynomials that we'll be talking about appear as solutions of Schrodinger equations. So not very central. Any comments on this that you want? So why don't we can go back to that later. All of you have seen this video. So why don't I just go through, and then if you have a question or something you're not knowledgeable about, then let me know and we'll talk about it. But the idea is that Sheffer polynomials is not a single polynomial, but it is a whole sequence. There's one of degree 1, and then 2, and then 3, like so. Actually 0, so there'd be a constant and such. Why don't we continue? And so the talk is in 5 parts. The first part will be about the answer, which is the objects combinatorially that we're constructing, which are I call pointed partitions. And then we'll talk about how we can derive them from the formula that I showed. Any questions at this point? Why don't we just talk about the objects first? That'll be the simplest part. So do you understand what it is to partition a set into 3 elements?
Yeah, sure.
Sure, you know. Bill, do you know how to do that?
Well, just from the example here, clear.
Exactly. So a set can have like elements 0, 1, 2. That's a set. And then the question is how to partition it. And so partition would mean to make it into boxes or parts, or later on I will call them compartments. So this is, and then the idea is that there are numbers that count this. So we proceed. And there was no choice to where to put the initial elements. So if you're building them, you go through, starting with the first one. This will become important. This very first compartment, which will be thought of as free space. But then when you have the second element, which I call 1 here because our counting starts with 0. Now you can choose. Do you want it in the free space, as I call it, or do you want to have a special compartment for it? Any questions so far? All okay. Then this is talking about how to put a second element in here. Okay, and then we can go back to this if we want at the end. But then this is explaining that I'm just using a different notation for what would be the normal set partitions. And this is how to put a third element. And once you put a third element, you can see that there are 3 things that you could be doing. And that'll give you the 5 kinds. And there's a general formula for here. So all of this was clear enough, or any questions up to here? Or any comments?
I mean, here in this recursion formula, I was not immediately sure how to get these different terms, why there's jkn and then k times jkn and so on. So this was not really that obvious for me.
Exactly. And so this is a kind of a slide where I put something that wasn't very obvious and I didn't discuss it much, but that the people who could understand it would kind of see it, they could stop it or not, the video. But what this is about basically is saying that there's an algebraic expression that says algebraically what's going on. But that algebraic expression, the objects have 2 indices. So for example, one index will tell you the number of boxes or compartments or parts. The other index will tell you how many elements go inside. So, so in the case here, we have 3 elements, and we can have, here we don't have any compartments. Here we have 1, here we have 1, here we have 1 compartment, but over here we have 2 compartments, okay? So this would, so then to go back to that slide, if there are, So how could I get two compartments, and how could I have three elements, right? How could I put in a third element for two compartments? Well, it could have come if I had two compartments already, and then I put the third element in the free space. That way, when I get the element, I'm not adding any compartment, right? So the number of compartments stays the same, but n goes to n plus 1 because I'm adding an element. But if the number of compartments stays the same, okay, well, then either I put it in the free space or I put it in one of the existing compartments. But there's k compartments. So like if there's k equals 2, if there were already two compartments, I could have put it in the one compartment or the other compartment. So there'll be one way to put it in free space. There'll be two ways to put it in an existing compartment if you already have two compartments. Let's look at that. So here I have my existing set with two elements, 1, 2, and now I'm thinking, how do I put the third element, number 3, here? And so suppose I already have two compartments. That would be on the very far right-hand side. The two compartments, there's a 1 in the one compartment and there's a 2 in the other compartment. And now I'm going to put this third element. Well, so one choice would be to put it in the free space, and that doesn't change the number of compartments. Another choice is to put it in an existing compartment, and then I have to decide, will it go in the one with the 1, or will it go in the one with the 2, let's say. And there's two ways to do that because you have two compartments. So if we go back here, the j sub k comma n, it would be, because k is 3 and n is we have n was 2, okay, plus 1 became 3. So if there's two compartments and two elements, then if you can add the free space, or there's two ways when you have two compartments and two elements to add it to one of the two existing compartments where k is 2. But there's a third way. The third way is to say that you add a new compartment. Well, if you're adding a new compartment and you want two compartments, you must have had only one compartment. 2 minus 1 is 1. So then you would have only one compartment, and then you would have two elements. So let's go back here, and that's what we'll find here. We have two compartments. Oh, we can have one compartment. Okay, and there's three ways to do that. You have one compartment, and then you add a new compartment. Okay, so you can add a new compartment here with the 3 in it, or you can add a new compartment here with the 3 in it, or you can add a new compartment 3 with it here. Okay, so there's actually three ways to do it because you had three ways to do it up here, and then you just add the compartment with the 3 in it. So if you add it all up, it says that 5 equals one way to add an element to free space. What is this? And two more ways to add it to existing compartments. And then here, or add to a new compartment, that would be, let me see. If I have two compartments and 3 elements, I could have had add it to the free space, or add it here, or add it here. Well, there was one compartment, there were 3 ways to do that. So, what am I've confused myself here. Let's see. Oh, well, you see, I got 6 ways because I'm wondering why to get 6, because we're going to get 15 in all. Okay, so that's the issue. So we're going to get these, actually 5 ways, because I add a new compartment to any of these 5. There's 5 here, right? Any one of them I could have had 5, plus the 2, plus this 1. So there would be 8 ways in all. 8 equals 1 plus 2 plus 5. Now I figured it out. Did that make sense to you? Did it make sense to anybody? A little bit, Kirby?
Yeah, it makes sense. Sure.
Bill, it makes sense to you. Okay, it makes sense to you. So I move on.
Well, if I compare it with the Bell numbers, I don't get the numbers that you're supposed to get. I mean, this is for me the part that is puzzling. I would write the recursion as k plus 1 times jkn plus jk minus 1n, and then figure out, is this really the recursion of the Bell numbers? And if I look it up, it doesn't look like it.
Well, okay, so maybe
So,
to clarify, let's go back here. Which Bell numbers? So the third Bell number would be 5, depending on how depending on how you look at it. But because you have to remember, I've thrown away the 0 element here. So if you have 0, 1, 2, that would be the third Bell number. So there's 5, but now when you have the fourth Bell number, there will be 15. There will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Of those 15, that's good, you should stop me. 8 of them will have let's see, hold on, go back. Oh, I made a mistake, Brian. So how many of them will have here 4 elements, right? 4 elements in 3 compartments. No, in 2 compartments, we said. How many will have 4 elements in 2 compartments? Oh, okay. Well, you have to look. So let's go back just and count them. 4 elements in 2 compartments, but in our notation, it would be 3 elements in 2 compartments. The point being that 2 compartments will have this 1, 2, 3. That's 2 compartments there. 4, 5, 6. Right. It's these 3 plus these 2 plus this 1 will be the 6 that we're counting. That'll be if there's 2 compartments. If there's 3 compartments, we will have this 1 possibility, right? If there's 1 compartment, we'll have 1 possibility here, 2, 3, 4, 5, 6. If there's no compartments, we'll have this. So I think that was something that would add up to 15, I guess, like 1 plus 6 plus 3 plus 6 plus...
Sorry, 1 plus 7 plus 6 plus 1.
No, there should be 1 has 3. How many have 2? 1, 2, 3, 4, 5, 6, right? So 1 plus 6. How many have 1?
7.
7 plus 1 has none, right? So 1 plus 6 plus 7 plus 1, right? That would be 15.
Yes.
Is that right?
Yes.
Okay. So for each of those, so these are actually what are called the Stirling numbers of the second kind. And if you add up the Stirling numbers of the second kind, like we just did, you will get the Bell numbers. And so this is kind of like breaking it down more refined. How would you add it all up? I think if you get the general idea, that's fine. But was that helpful? Is that?
It still confuses me. But
Okay.
I mean, it's the formula that confuses me, not the idea that you want to go to. So
yeah, so we'll so we at least we're not going to maybe get to 100% understanding. We're just trying to get 10 or 20% more than we had. So that was the objects. Any more questions about the first part, about the kind of objects we're building? There are these pointed partitions, and then the crucial thing later on is going to be that we've thrown away the 0 element, right? That'll be called free space, okay? So these 2 aren't in a compartment, but they really kind of are if you think of there's a 0 in here and then there's a compartment we would draw. We just don't draw it, okay? Any questions? Now we move on to the next part then. And so the next part is the generating function. So now it becomes, from combinatorics, we're going to algebra. And this is the algebra that we have. So we're going to try to understand this equation where on the one hand, we have these polynomials. So the first polynomial S0 of x will be just a number like 1. Actually, we tried it. But the next one, S1 of x, will be a polynomial of degree 1. That'd be like x plus 3, for example. And then S sub 2 of x could be something like x squared minus 4x plus 7, depending. But it'll be a polynomial of degree 2. Now, in the case of Sheffer polynomials, you add these t, so it'd be t naught, t squared, t cubed. These are kind of like helping to organize this whole thing. And it turns out if you do all that, you have a whole other form for writing it out, where all the x's can be thought of as participating in this exponent. And you take x times a generating function u of t, and you take it e to the x u of t, and then you will multiply it by another generating function here. So this is what we're trying to understand. And this is what these generating functions look like. Any questions here? I'll go to the next slide and you'll stop me when. So these are examples of what these generating functions could look like in a particular case, like the Hermite polynomials or the Laguerre polynomials. And then this is some, what we're trying to get intuition about. But basically, the compartments, each compartment will have a weight x. So all the stuff with compartments is coming from up here on top. And the free space is this extra thing. If there was an x here, then it should be able to get a way to climb it up there to the top. But there's no x here. So that's kind of like what makes this free space really mathematically distinct and maybe physically distinct. Okay, and then this is what we're going to be, this is like the Sheffer polynomial, how we're writing it out. So like I said, you have degree n would be x to the n, and then there's terms of smaller degree, and then that'll tell you how many compartments it has. Okay, and then we're going to multiply all this out. Is this understandable, or do you have any questions about this? Everyone is fine with everybody? So what we're going to do is we're going to see how this goes. But the crucial thing is that we're trying to understand how to get a single element on the left-hand side. What would it look like over here on the right-hand side? What is it encoding? And so it's this coefficient t to the n. If we took it on the left-hand side, we would focus on this Sn of x. But on the right-hand side, we need to pull it out. We're going to see what we're getting. We're going to get some kind of expression. Basically, the terms of the polynomial. So, but it'll be coming from a contribution. So we'll be getting some part of it will come from a of t, some t to the n minus k parts, and some part will come from the e to the x u of t. And are you all familiar with this? Bill, are you familiar with this expression that e to the x something? It's going to be like 1 plus x plus 1 over 2 factorial x squared plus. Are you familiar with that formula, Bill?
Other than here, not recently.
Okay, that's a formula that's very famous, but that's a calculus formula. Okay. Any questions about this? This is what we're shooting for, to connect what we're doing there with this. And then I'll go through. And here's this part where I explain how we're going to try to interpret this. There's some obstacles, let's say. We need to rethink it. So there's a 1 over n factorial. And so that's what the generating function is. And now we're going to calculate it. Any parts on that that you want me to go back to, or do I just jump into calculating the kth derivative? We'll see. I'll continue then. You have to stop me if you want. So when we have a generating function, we're taking a derivative, right? What is that going to do for us? Well, one of the things is that first of all, there's a thing called the Taylor series. So if you've taken calculus, you're familiar with Taylor expansion, or it's called the Maclaurin series in this case, because we're expanding around t equals 0. And so instead of just u0 plus u1 t plus u2 t squared, we're actually, it turns out that these are encoding certain numbers. And you can actually see that if you take, for example, if you plug in t equals 0 here, and this will all go to 0 except for the first term. So u of 0 equals u0, right? That's the issue. Now, if you take the derivative, all of these derivatives, well, the u0 will go away, but now instead of u1 t, you'll have u1, and by a very similar logic, you will get like u prime of 0. And if you keep taking derivatives, what will happen is that you'll get like 2 times u double prime of 0 equals u2, and so u2 will equal u prime over 2 factorial. So this is what we're making use of. And what that does is that then that introduces these 1 over m factorials here. And that's very nice combinatorially, because it'll be able to combine them. You can multiply an n factorial, but you'll be dividing by all these things that build up to n factorial. Well, that's a multinomial coefficient. Okay, and then you'll get these multinomial coefficients. And so what that does is that it makes all of these compartments, you can imagine them as having different elements inside. And it's crucial that once you know that they're distinct, you're able to reorder them, for example. A problem with reordering is if you had two numbers that were the same. Okay, so that's what this is all about. I don't know if you want to go into that, but this is and so what ends up happening here is that you take the nth derivative and you'll get n factorial Sn of x, which is what we want. And then here we're using, let's see. Oh, in order to take, when we start taking these derivatives, so the point is that we know how to isolate this Sn of x on either side by taking the derivative and then by setting t equals 0. So we know how to do it on the left-hand side, how to isolate it. So if you take the same actions, what will you get on the right-hand side? Okay, you'll just need to take the nth derivative, which can seem very kind of daunting, but if you know the chain rule and you know the product rule, that'll be possible. Any questions up to here? So here's a concept that I like to think about, analytic symmetry, which says that when you take the derivative, if you get something back or something kind of like what you got back, it's symmetry. Here, we're starting to go through the derivatives, and we need to use the initial conditions also, because we'll be setting to 1. And here I introduced this concept of the mother function and the baby function. So if you take the derivative of something like e to the x u of t, you will get this back times, by the chain rule, you'll get this back times the derivative of x u of t. Well, x is, with regard to t, it's a constant. So x u prime of t is what you'll get. So you have your mother function plus what I call a baby function. And so you start to, and this is the product rule. And so we can start to use the product rule, how it looks like. And the crucial thing about the product rule is that if you have lots of terms that are multiplied together and you take the derivative, you're going to get the sum, but you will get each factor differentiated once with the other factors kept the same. So they have some combinatorial regularity. And so if you look at the derivative of you look at the second derivative, you'll get 5 what I call pedigrees, basically 5 terms. And some of them can combine, but basically you'll get 5 different things. They'll combine to get 4 terms. So we set, and then we set t equals 0, and you can see that when you set t equals 0, you're going to get a polynomial here. Okay, so we're on track. Then you can get 15 terms, but which I call pedigrees, let's say, because there's 15 ways you could be unfolding these things, and then 8 terms will come from combining them together, and you'll get a polynomial of the 3rd degree, let's say, in this case. And then you start to see the pattern of what's like the father factor, the baby factor, the mother factor, that the A of t is like the father factor. And so the A of t just gets repeated differentiation however many times, but it doesn't ever have a baby, so to speak. It doesn't add more, but the mother keeps adding babies. Any questions up to here? And so then at this point, I was able to, it looks so complicated, but I was able to cheat and use this online encyclopedia, and I plugged in 1, 2, 5, 15, because that was the number of pedigrees, as I call them, and it spit out this possible series, at least the most likely one on top, the most famous one, Bell or numbers. And so then it told me, oh, this is the number of ways to partition a set. And once you know that, then you can try to use a combinatorial argument to explain that this is how to think about this, how this is connected. So now we're going to say that, well, when we have 15 pedigrees of these terms, then we'll have 15 pointed partitions, right? And so then when you do, and so you have to, this is a little bit sophisticated in the sense that we're going to have a bijection where you have objects on one side, or like in this case, mathematical expressions on one side. We're going to have like combinatorial objects on the other side, but we're going to say they go match up, that for each one of these, there's one of these and vice versa, and you can go back and forth. That's a bijection. But we need to establish this by induction on n. So induction is like a ladder. So we'll first start, well, is it true when k equals 0? Well, that's trivially true. I mean, there's just one term here, a of t, e of t, and then we just have one term when we have the free space or the empty space, which have the original term. That's almost too easy. So sometimes it's nice to look at the next case k equals 1. it's saying when you take the first derivative, there's two ways. There's going to be two terms, because you take a prime of t, e of t, you're going to take a of t, e prime of t. And they correspond to two possibilities with these pointed partitions that if it's a prime of e of t, it'll match to this one in free space. But if you do the e prime of t, you get an x, and then that'll mean that there's a compartment. So we do case k equals 1. So then you jump to the case 10, let's say n equals 10, right? Or n equals 1,000,000, it doesn't really matter, or n equals 1,000,000,000, right? And if you can go from n equals 1,000,000,000 to n equals 1,000,000,000 plus 1 in a regular way, so basically from n to n plus 1, then you can just go all the way up to infinity as far as you like. So it's a little bit sophisticated, but we need to know how to match this pedigree. This pedigree is like a history. We'll match that with these pointed partitions. So the mother actually doesn't have to match to anything because the mother doesn't really show up. And when you set t equal to 0, e of 0 will just be 1. The mother is always staying the same. Now the father may get differentiated like j times. That'll mean that there's j elements in free space. And there's babies. Now there could be the number, so each baby can be differentiated L sub I times. That'll mean there's the ith component will be, the ith compartment will have L sub I elements. When you add up this j plus L sub 1 plus L sub 2 all the way to L sub m, let's say, if there's m babies, then it should add up to n. And then the idea is that we're trying to show that you can go back and forth between these two things. So, and the way we do that is we differentiate here, we differentiate the father is the same as adding a new element to free space. Differentiating the baby is the same as adding an element to the ith compartment. Differentiating the mother is the same as adding a new compartment with one element, which is the three cases that we work through. And so this is tracking. Here's an example where we track that. And here just basically it's the same issue like we're trying to go through. And it just kind of shows like if you really wanted to do this constructively, then you would have to write everything out here. Which order, which ones did you differentiate when? Okay, so so that's that. And then this is basically explaining how the bijection works. And then finally is the significance. Anything, we have about 10 minutes and maybe we'll have enough time to finish. So any questions about significance here, or any questions up to here now? Maybe I'll just stop and ask for what were the things you'd like me to explain? But so maybe I'll just say, what do I think is significance? One is that this idea of the father, the baby, the mother, that relates in this language of wondrous wisdom with the one, many, all. And if you've seen the introduction to Math for Wisdom, I talk about the minimization operator mu. That's in a completely different situation, but you get the same cognitive framework, but you get different intuition in different cases. What could that possibly mean? So then another thing is that in the wondrous wisdom, there's a deeper structure called the learning cycle of or I call it the threesome. You take a stand, follow through, reflect. And the idea is that there's 4 conceptions. They would be necessary, actual, possible. They would be object, process, subject. They would be one, all, many. They would be being, doing, thinking. So when you want to conceive it concretely, you pick one of these ways. And so this is one of the ways it comes up. Now, but this learning cycle, if you look at Lie algebras, it comes up here. Oh, good. Speak, Thomas. Yeah.
Yes. Here, to some extent, you lose me when you want to compare the Jacobi identity, how that really is related. I don't see it. That's my problem.
Okay. So with the learning cycle, it's just a permutation of 3 things, right? In a certain sense. It's a 3 cycle. So an example of the 3 cycle comes up in the Lie algebras, in Lie theory. Lie algebras satisfy, the elements of Lie algebra satisfy what is known as the Jacobi identity, in which you have this Lie bracket and you go, well, take y and z, then put x with the y and z. That'll be one way to organize it. Or you could do the z and x and do that with the y. Or you could do the x and the y, do it with the z. And when you add all these together, you get 0. So they kind of like balance each other. So this type of 3 triality or whatever, but in this type of cyclic form, it comes up here. Now,
But
why
I
am I
don't see
saying that's relevant?
this identity, because if I look at the identity, it's just mathematically summing up to 0 identically, whatever you do. As long as
It's kind of, it's not hard to see if you're familiar with this and you know that the Lie bracket in the case of matrix algebras, matrix Lie algebras, it would be yz minus zy, for example. If you multiply it out, you know, you would get that. But maybe I think one crucial thing about here then is this, that if you remember, and I'll have to go back and find it, but if you remember the whole Sheffer formula, it looks like a of t times e to the x u of t. Well, that is very much the kind of way that a Lie group looks like with respect to its Lie algebra. So in the Sheffer sequences, there is a suggested connection with Lie theory that I'm exploring. See, so now all of a sudden, this 3 cycle, which suggests itself, and the 1 all many, which is coming up in the Sheffer sequences, there may be a connection here. So that's the kind of thing it makes me excited to say, you know, can I connect that? Does that satisfy you, or Thomas? Or
it satisfies me that you find a connection. I just don't see it. So
okay, fine.
I will have to wait for your insight, and
right.
with more explanation, I might get it too, but it will take quite more time.
Okay. And then let's see. The next is that, okay, another important thing was that here we could have, it would be all the same numbers if we would have worked with partitions of sets, but I emphasize that we want to think of these as what I call pointed partitions, which means that we threw away the 0 and we threw away the first compartment, and we have this notion of free space, you see. Now, there's a couple reasons why that is important, in the sense that, like, when you look at a polynomial, n of the terms have x's, but there's an n plus first term, which is constant. And see, so when you look at how the math works here, n of these, you know, the compartments have an x, but there's something that doesn't have any compartments. See, so there's something natural in terms of having this father factor, right? People could say, why do you need the father factor? But that's what's showing up here, and it also shows up as the a of t. Another thing is this choosing 1 out of 1. That is something that comes up in a very mythical thing, this field with 1 element. So that's a thing for future thing. If you like, you can stop me on any of this, but this distinction between ordinary generating function and exponential generating function, that was important in order to make the combinatorial interpretation work out smooth. And then we're going to have future videos about orthogonal Sheffer polynomials. And that'll relate to this cognitive framework for decision making. And that'll be relevant for probability and statistics because the exact same thing happens there. And here is an example, concrete example, Hermite polynomials. With the Lie theory, there's this notion of covering space and root lattices and root systems and how they fold up. And I think that's basically it. So maybe we can end in a few minutes. Just, is there anything anyone would like to say here? Or we can continue a little bit of discussion. Maybe if we could continue, I think if everyone just who'd like to just kind of spoke about what they found interesting or what they would like to learn more. Who could, Kirby, do you have a comment or thoughts?
Yeah, when I look at these kind of things, given my background as a programmer, my impulse is to do an example with a discrete n that's higher than just, you want a computer at your elbow, like n equals 10 or something, because your partition space it gets big real quick. But just work through the whole thing, top to bottom, as special case as I could. That's what I would do.
That makes a lot of sense. Other and I'll show something I've brought that's make it more concrete. And who else has a comment?
Yeah, I'd like to say a few words. Anders is my son, and he asked me to participate, but I have an engineering background, so I know some calculus, some differential equations, but this requires another level or two of maturity in math that I don't have, and I can't comment. So thank you all for joining Anders in this challenging presentation and maybe future discussions, but it's a little bit beyond me.
Okay.
So Andrew, thank you very much for inviting me.
Thank you,
But,
Dave. I'm very happy that you can see this,
Yeah.
so I applaud you. Thank you. Who else? Thomas?
I just wanted to thank your father too of following and seeing.
And maybe I would like to ask Bill if you would say a few words, because also for Bill, well, he has maybe, you know, his background also is maybe even less in math, but he really put effort to.
Yeah, I'm slowly things will click. You know, obviously this is powerful stuff, and you're, you know, bringing it to us. It's your thing, but you know, your challenge is to pass it on. I'm gonna stick with you on this.
Fantastic.
At some point, I'll catch up along the way. But I wouldn't be any. I would be at the same level as your father in where we are with this. But hey, that's the challenge of it.
So, and maybe for last, Raimundas, any words to add?
Sheffer polynomials, combinatorial spaces, quantum physics, first are outside of the scope of my professional interest. Second are way over my head. So I cannot contribute something mathematically valuable to this discussion.
Okay, so I just want to thank everyone then, and just to conclude with a prayer of thanks, that to have people who could come together, and you can see I'm just learning how we can interact. But we continue on this. Thank you very much.
thank you, Andrew.
Okay.